Okay, well, here we go in lesson 2.2. I hope the practice in 2.1 there, what was it, 1 through 11, gave you some experience of working with calculation of probabilities. In this lesson, we kick it up a notch, actually, and talk about compound and independent events. And you can see here there are 4 different objectives for the lesson, and I'm not going to read through each of those right now. But I think the key here is found in the title of the lesson, compound and independent events. Think of those 2 adjectives, compound and independent. So we need to think about what those mean. So you've heard this word compound before, like compound sentences in your English or literature classes. Compound means the exact same thing in probability here. Compound really means it's plural. It's more than one. So if we think about that, there's going to be something happening, and there's more than one part to it. Like now, instead of rolling a die and asking about the probability of rolling a 2, now maybe you roll a die 3 times. And what's the probability of rolling a 2 and a 2 and a 2? So the compound just means more than one. And then it's going to be crucial in our calculations now to think about what independent means. And the nice thing about that is it means the exact same thing that it does in other places. So you can already answer this question, right? Okay, so whenever all of these situations now are going to have, there's going to be more than one thing going on. It's going to be like stage 1 and stage 2, like drawing a card out of the deck and drawing another card out of the deck. It's a compound situation then. So when those compound events occur, we have to ask ourselves, does the outcome of one part of the event influence the outcome of the other part of the event? And if those parts of the event do not affect one another, then we call those independent events. They're independent if they stand alone, is maybe a definition you've heard before for independent, that the outcome of one will not influence the outcome of the other, then they're independent. And then if they do affect one another, then they are dependent events. So dependent means the outcome of one part of the event will affect the outcome of the other. And so when we do our calculations, we have to distinguish whether the outcomes are dependent or independent, and then work with the numbers accordingly. There's a little video clip that normally I would show in class, and it's Mr. Kahn, Sal Kahn from Khan Academy, and he's talking about a really simple little example with dependent and independent events. And I can kind of mimic that. There's going to be 2 prizes awarded to a group of people. It could be 30 people, could be any number of people. Each person can only win once. And I ask, are the outcomes independent of one another? And Mr. Kahn has a knack for describing things and making complicated things easy. And his explanation says, think about this. Think if there's only 3 people, person A, person B, person C. And person A is chosen to win the first prize. So person A right here wins the first prize. Now think about who can win the second prize. Now it's people B or C. It's only these 2 persons here, these 2 people, that can win the second prize. Now think of this scenario again, where we have person A, person B, person C. Maybe person B wins the first prize. And if person B wins the first prize, who's eligible to win the second prize? Well, that would be person A and person C. And we have a different possible outcomes for the second prize. So in this case, these two events are not independent of one another. They are dependent events because the outcomes for the second prize depend on who was chosen to win the first prize. So they are not independent events, they are dependent events. One thing that I don't like about the online text is they assume that we're all familiar with a deck of cards, and I know not everybody is. So maybe if you're not familiar with a deck of cards, you might want to download or an image or even print off an image of a deck of cards. Here's our deck of cards here with 4 different suits. The suits are hearts and diamonds and clubs. Wow, how do you draw a club? Kind of 3 clumps to it. A club and a spade. What's that? Kind of like that. So there's 4 suits and there are 13 cards. There's 13 cards in each suit for a total of 52 cards. And so if you're not familiar with a deck of cards, you'll be at a little bit of a disadvantage here. So let's look at a couple of examples quick in this video of compound events and calculating the probabilities. Noah has 8 different hockey sticks to use for games. 5 of those sticks are wrapped with black tape, like you see in the picture. Suppose Noah randomly grabs a stick from the bin, the stick bin, and then he grabs another stick from the bin, and he brings those sticks to the away game. What is the probability that neither of them are wrapped with black tape? Well, when you do your calculations now, even though it's a compound event, because he picks 2 sticks, do 1 at a time. So let's just do the first stick. So there's 8 different sticks in the bin, and 5 of those are wrapped with black tape. So what is the probability that he does not get a stick wrapped in tape? So let's see, if 5 of them are wrapped in tape, that means 3 out of the 8 are not. So he's got a 3 out of 8 chance of getting a stick that does not have tape on it. Okay, now, second stick. What's the probability that that second stick is not wrapped in black tape? Let's go back. 5 of these have black tape on them, right? And 3 of them don't have tape. And the first stick that he grabbed, we're supposed to assume did not have, he grabbed one of these 3, so, and removed it. So now there's only 2 left, right? So the probability that the second stick also does not have tape is dependent on knowing that the first one came from this group of 3. So it's kind of a dependent situation, but anyway. So out of the 7 sticks left, how many don't have black tape on them? Well, it'd be 2 out of 7. And so the probability that he gets neither of them with black tape is going to use the fundamental counting principle, and now we'll multiply and say the probability of getting this done and this done is, let's see, 3 times 2 is 6, 8 times 7 is 56. There's a 6 out of 56 chance that would happen. And you could simplify that fraction. You could put it in decimal form if you wanted to. I guess I have a calculator here to get a better sense of this. 6 divided by 56 is approximately 0.107. So he's got about a 10.7% chance of grabbing 2 sticks, and neither of them are covered with black tape. Here's another example. Kayla is working at Black Bear Casino. She's the dealer there. There's Kayla in the picture. And she's going to deal out 2 cards to the sole player on the blackjack table. What is the probability that those 2 cards are of the same suit? I'm going to admit right now, this is maybe not a good example because it's a tricky situation. So 2 cards the same suit means, for example, they're both hearts. What's the probability they're both hearts? Or it could be any suit. What's the probability they're both spades? And so think of it this way. If you want your cards to be the same suit, what does your first card have to be? Well, actually, that first card could be anything, right? So all 52 cards are favorable. All 52 are good. So for the first card, any card, 52 out of 52, they're all good. Okay, so now let's say Kayla deals out a card to that first player. And let's just say, for the sake of the example, that that card was a red, should be red here, a red diamond. Okay, so let's think about that second card. How many cards are left in the deck? Okay, 51. And out of those 51 cards, how many of them would be diamonds? See, originally there were 13 diamonds, right? But she's dealt one of them away, so there's 12 diamonds left. So the probability that second card is also a diamond is 12 out of 51. And if you multiply here, you multiply numerator times numerator, denominator times denominator. But really, this is just 1, right? And so we end up with 12/51. Actually, those are both divisible by 3, right? 4, I want to say 17ths maybe, 4/17, a little less than a 25% chance. Here's another example, a better example maybe, compound event. This is compound because if you read the problem here, we're going to distribute 3 pieces of candy. And so if you're randomly, without a pattern, if you're randomly distributing candy, what's the probability of the first piece you distribute? Oh, wait, let's read the problem here. What is the probability that all of the first 3 pieces distributed, they're all going to be milk duds? What's the probability if you randomly reached in here now that you're going to get 3 milk duds? Well, let's do it one at a time. What's the probability the first piece is a milk dud? Okay, 10 out of 40. What's the probability the second piece is also a milk dud? Don't forget now, you've removed 1. So now, out of the 39 remaining pieces, how many would be duds? Okay, 9. And then we'd have to do an 8 out of 38 also, right? Now, to save time in the video, I'm not going to multiply, but you really should multiply these together then, and you'd get your probability that all 3 pieces will be milk duds. In this example, there are 8 balloons. You can see a picture of that. There's 8 balloons. 3 of them have a winner tag on the inside. And you can't really, like in the image here, you can see the W's, but in reality, you don't know which 3 have the winner slip inside. So you throw 3 darts and you pop 3 balloons. This question, this compound related question is asking, what's the probability that you hit 3 balloons and all of them would be marked as a winner? In other words, what's the probability winner, winner, winner? Okay, so let's think about it. Let's throw the first balloon. How many balloons are there? Okay, how many of those are winners? So the probability of getting a winner is 3 out of 8, right? So let's assume we throw and we pop a winner. What's the probability of getting a winner now? Okay, and then a winner on the third one. And then once again, we'd multiply this together. Find the product of those three values. 3 times 2 times 1 is 6. 8 times 7, 56 times 6. 56 times 6. I think that's 336. So you got a 1 out of 336. Excuse me, 6 out of 336 chance, which is not very likely, right? Okay, one last thing in the lesson, and now we're changing flavors a little bit in that we're working with percents now, and we don't even know what the total number of things are, items are. Like in this example, we knew there were 8 balloons at the beginning. Here we don't even know how many people there are altogether. So we work these a little bit differently. So 12% of the people are left-handed. So what percent of the people would be right-handed then? Okay, we'll assume there's no ambidextrous people. All right, so 88% are right-handed, 12% are left-handed. Let's keep that in mind. If we randomly select 3 people, what is the probability that all 3 would be lefties? All 3 lefties. All 3 come out of this 12%. So the way we do this is we take 12%. I'm going to do this on my calculator, so I'm going to convert to decimal. I need somebody out of the 12%. I need the second person is also a lefty, and the third person is also a lefty. So I multiply 0.12 times 0.12 times 0.12, or in other words, 0.12 raised to the power of 3, which is 0.001728. Oh my gosh. If I slid that decimal point over, I've got like a 0.1 or 0.17% chance that they'll all be lefties. Not very likely to happen. Follow-up question. If we randomly select 10 people, what is the probability all 10 would be right-handed? Well, remember the 88% of the people are right-handed. And so I need 10 people. I need there's one right-hander. Here's another right-hander, and I need 10 of them. So I'm going to go 0.88 times 0.88 times 0.88, which is 0.88 to the power of 10. And my calculator says I'm going to change that to approximately 0.278, about a 27.8% chance that they're all 10 are righties. Wow, does that make sense in your brain? If you pick 10 people, the probability that all 10 will be right-handers is fairly low. If you've got 10 people, it's fairly probable that there's going to be a lefty mixed in there. One more example real quick. Statistics show that 3% of junior students will not take the ACT test. Of course, now with this virus thing going on, that's totally changing, but let's pretend it's a normal year. Okay, so normally 3% of our students don't take the ACT. 97, that means 97% do take the test. Okay, what's the probability that if 5 students are chosen at random that all 5 juniors will be taking the test? So what percent do take the test? Okay, so there's a person taking the test. There's another person taking the test. and we want all 5 people, that's a 7, we want all 5 people to be taking the test. So 0.97 raised to the 5th power is approximately 86%. So it's about 86% that all of them are taking the test. Now, read the questions carefully, because just tweaking it a little now, what is the probability that none of them are taking the test? Well, that would be 5 of these, right? 5 of these people, and 0.03 to the 5th power is gotta be pretty close to nothing, right? It's gonna be pretty close to 0. Not that you would remember because you didn't know, but you're going to have a quiz following this lesson. The quiz just covers lessons 2.1 and 2.2. So lesson 2.1, the last lesson was working with basic probabilities where there are no compound events. And now we have compound events where it's kind of a plural situation. There's more than one event going on. And then it's important for you to distinguish in your calculation whether those events are independent or dependent. And if you can do that, you're good. So let's look at one quick example and then we're done. So I roll one more example. I roll a die twice. What's the probability of rolling a 5 both times? Well, this is a compound event, right? Because we're rolling twice. And does what you get as a result on the first roll affect what you get as a result on the second roll? Okay, so since they don't affect each other, they are independent. So it's a compound event. They're independent of one another. Let's actually do the calculation. So what's the probability to roll a 5 on the first roll? Okay, you got a 1 out of 6 chance. How about on the second roll? What's the probability of rolling a 5? Well, that's also 1 out of 6. So you've got a 1 out of 36 chance, about a 3% chance of rolling 2 5s in a row. Okay, we're gonna skip through a couple of these screens. The video's getting long already. We've already seen that. Okay, so your assignment, you see it on your Schoology assignment as well, but from page 43, this is going to be in problem set 2.2, and I'm going to ask you to do 1 through 13 and submit that to me. So it's page 43. It's exercises 1 through 13 of lesson 2.2. And this, you can see the page right here. And there's multiple parts to some of those problems. So it'd be 1 through 13, page 43. So give it a try. Compound and independent events.